I get to kind of talk about something fun here, which is looking at electrical signals in the brain with behavior. So detecting and targeting natural behavior with the subthalamic nucleus brain signals. So the thought behind this is really deciphering or decoding brain activity from these signals. When we put a DBS lead in place, we're able to record not only the neuronal cellular recording, we're also able to record kind of waves, kind of like an EEG, except it's at the depth. And you can see kind of a little snippet of the signals there recorded from each of the 4 contacts from the DBS lead. So the question is is there value or is there information in this signal that can lead to us detecting what the patient is doing at that time? And why would we do this? There are, even though DBS works fantastic, there's lots of class 1 evidence that shows that DBS works remarkably well for Parkinson's disease. We may want to apply DBS to other neurological indications that it might be a little bit tougher. But also there are some side effects with DBS even for Parkinson's disease, and I kind of outline a few of these here. It's a little small, but speech intelligibility is one recognized side effect of DBS and the subthalamic nucleus. Some cognitive changes, potentially with verbal fluency, and then gait and balance disorders. So those are some of the examples of some of the side effects that we see in DBS, especially in STN. And these might be behavioral dependent. So if somebody's having a difficult time talking, maybe there could be a special DBS program for speech. And then if that patient switches into a different behavior, like walking, gait, some kind of gait, maybe that DBS system could detect that and then switch into a different kind of program to reduce those side effects. So it's kind of a closed loop, behaviorally driven DBS is what we're after. And that's kind of the outline here in this diagram. So currently, walk into the neurologist's office, we get programmed, patient leaves, tries it out for a couple weeks, comes back and says, I have these issues, can we kind of adjust? But it's a very static process, and I think it's difficult for the physicians to determine in a 1-hour visit the right programming parameters for all of the behaviors that person is going to go out and do over the next years. But if we're able to somehow create a detection algorithm and self-adjusting algorithm, then that could potentially help those patients. So we're really using the local field potential as a control signal for detecting behavior. And these next 2 slides are, I stole them from a colleague of mine, Kai Miller, but he explains this really well of some of the basic frequency analysis that is so common in this type of work. So this is an epilepsy patient with a grid in place, and we're able, from one location on that grid, we're able to record some voltage, so a voltage over time recording. And it's a wavy line, and the waves are a little bit sharper at some points and a little bit wavier in other points. But we can break that more complex wave up into different components, and each one of these different components has a different frequency. And instead, if we change the language from when to how often, we're able to create a separate power frequency plot. You can see the blue plot here, where the frequency is a little bit to the left, which is a lower frequency. The red is a little bit higher frequency, so it's shifted a little bit to the right. And then the green is a little higher frequency, so it's shifted to the right even further, and even higher. And so when we create a composite of all this, from our original signal, we're able to break that up into different frequency bands of different strength. And that's really what the next analysis is about. And also with the cortex, with the motor cortex, when we're recording from the motor cortex and we do a behavior like hand movement, where'd that little pointer go?
Maybe on your computer there as well.
Oh, this is it. Yeah. So uh, this is a rest, and there's a bump here. We call this the beta bump, and then this little bump here is 60 hertz. So that's like line noise from our power supply. But this is the beta bump, and when people move, like a hand movement, that beta bump diminishes. So you see the change here of the beta bump diminishing with movement. There's also an increase of power or increase of the energy in the frequencies that are higher. That's called gamma frequency. This is called beta frequency. So we're able to recognize that in the motor cortex, but we're also able to take that to the next level into the subthalamic nucleus as well. So this is a recording from a patient, a single patient, where we have the DBS electrode in the subthalamic nucleus. These two are my estimation of where the recording electrodes are for this particular graph. And this is basically a power spectral density that's expanded over time. And so we use color to code the relative changes in strength. And to the eye, there's this big blue blob here. And what that big blue area here is actually in the beta frequency range, which is from 13 hertz to 30 hertz, which is beta frequency. And it corresponds to time zero over here. Time zero here is when the patient starts talking. This gray is a microphone of their speech. So when they start talking, the beta diminishes, and when they stop talking, there's actually what we call a beta rebound. There's increased power in that beta frequency band. So we're able to recognize those patterns. And blue here just means a decrease in power or a decrease in those frequencies. And it's very location dependent in the STN. So this is also a speech task, and we have spectrograms over 6 bipolar pairs. So if we have 8 contacts in the brain, if we subtract 1 from its nearest neighbor, then we end up with 3 on each side. And you can see that this left STN electrode 3, which is in the dorsal part of the STN, gives us the biggest beta effect that we see for speech. So it's very location dependent. And this might have some implication of when we're designing closed loop DBS systems in the future. It might not work so well to just put in our DBS as we do standard and hope that we hit the right spot for the closed loop signals. It may actually have to be driven. The electrode placement may actually have to be driven by signals in the operating room to make sure we're in the correct location. So that's the background. So the next step of being able to, we recognize that there are these patterns, but can we detect these patterns in some kind of automatic fashion? That's the next challenge. Can a device detect these changes and then react to it? And you can see here, these are 2 different behaviors. So at the top, there's speech. The bottom, there's movement. We're kind of cheating here a little bit. I'll tell you that up front, because speech is, they're talking a whole lot longer than they're actually pressing a button. So take that. But this is, you can imagine here, if we draw a box around the behavior, for this speech behavior, and we draw a box around this behavior, which is pressing a button, you can see the patterns are quite different, and we can create mathematical computer algorithms to detect that difference. And those classification methods are 2 common classification methods are support vector machine and k nearest neighbor algorithms. And a support vector machine, I'll explain this one. A support vector machine, we take the real data. So that real data might be the image that I showed you on the previous slide, that nice colorful image. That's our real data. We run it through some kernel, which is just a fancy mathematical function that expands that data into some kind of n-dimensional space, which is so taking input space into some increased dimensional space. And then this support vector machine is able to try to predict some kind of line in the sand that separates one set of data from another set of data. So one set of data being the speech data, another set of data being the hand movement data. So that computer algorithm tries to create some kind of line in the sand, which is called a hyperplane. And then if the data falls on one side, we call it one movement. If the data falls on the other side, we call it the other. And then we can determine how accurate our classification methods are. And they're actually reasonably good. So these are across 14 different patient recordings, so different patients. And these are both support vector machine predictions, but we use different kernels, different mathematical functions to expand that data. And the accuracy is, sometimes as high as almost 90, but more typically kind of in the 60% range. And if we kind of look at different classes, if we classify speech versus motor, speech versus just a random noise, or all three classes, we're able to, with different classification methods, able to get our accuracy kind of up into the 70s and 80s% range. So that's using a single type of kernel, which is that mathematical algorithm. Now there are a whole slew of different kernels available to use, and it's hard to predict which kernel is going to be giving us the best classification results. So what our engineering group decided is, well, why don't we use multiple kernels, and we'll let the computer algorithm kind of decide which kernel is best for any given patient recording. So that's called multiple kernel learning, and there's lots of fancy math here that I don't have time or the know-how to go into all that detailed. But it's basically that. It's taking multiple kernels and weighting each kernel according to its accuracy. And when we do that, so this purple line here is the multi-kernel learning. It gives us much superior results across patients above the other individual kernels. And we're able to classify with reasonable accuracy, button press, speech, just random noise, arm movement, or mouth movement. And so that's kind of where we're at with classification. We're now able to recognize these patterns. But the next step is how does the machine know when that behavior happens? So all of this classification is us telling the computer algorithm there's a behavior here. Please let us know what it is. But can we then go to the next step of having the machine say, hey, now there's a behavior. Let's pass this off to our classification algorithm and see if it can figure out what's going on. And we do that by recognizing that the left brain and the right brain signals are actually in sync with one another. These are spectrograms of a button press. So this is a left button press and a right hand button press. And this is the left subthalamic nucleus recording. And this is the right subthalamic nucleus recording. So you can see, unlike motor cortex, when we press a left button, both hemispheres react, or both hemispheres are really involved in that planning. And we press a button with the right hand, both hemispheres are really involved in the same level of planning. So there's a synchronization there between the hemispheres. And that led us to wonder if we can just measure that synchronization between the hemispheres. And does the synchronization change at the time of a movement? And it turns out it does. So we're able to take the left LFP and the right LFP channels, do a nonlinear regression between those two channels, and basically what happens is there's an increase in the correlation between those two channels at the time of the behavior. So that allows us to actually detect a behavior and then pass it along to our classification. So I'll skip some of this in the interest of time here. And this is a result. These are the results of our detection algorithm of detecting a behavior when a behavior actually happens. These are the receiver operator curves of true positive rate here on the y-axis and a false positive right here on the x-axis. And the diagonal line is just chance, random chance. So you can see that some patients perform very well with accuracies, area under the curve of about 90%. But there are other patients, and this may be something to do with the patient characteristic, or it may have to do with our lead placement not being ideal for this type of analysis. But some patients do not so well with this type of detection. So there's a significant variability here, and we can see that across subjects. We can have accuracies up to 90% for detection, but down into the low 70s also. So that's that type of data analysis is performed on intraoperative data when patients are in the operating room. Wires are in the brain. We're able to hook those wires up to an amplifier system. Patients get a particular behavioral paradigm. Our next step is really implanting a device that's able to record brain activity and being able to take that analysis outside of the operating room into a clinic setting or even potentially into the home setting and be able to access these signals to see what the signals do in medication on states and off states and a whole variety. It really expands our opportunity to be able to look at these signals carefully. And I think we're sort of time.
You've still got about 10. Don't worry. We can go to questions now. Absolutely.
Okay. I still have. So I can show you a little bit of our data here.
The clock will start counting down at 10, so I'll come up at 5, just so people know.
Okay. Okay. Fantastic. Okay, it'll move. Okay. So these are our power spectral densities in the operating room versus this Activa PCS device. So we wanted to determine if we get the same data from in the operating room when we have wires in the brain hooked up to expensive medical amplifiers versus an implanted device that patients carry around with them. And we can see across these 7 subjects, the dotted line is the power spectrum just at rest in the operating room recording, and then the solid line is the implanted device. So you can see this patient here has a significant beta bump, and that beta bump is thought to be pathological in Parkinson's disease, where this increased strength of the beta frequency may lead to some kind of poor control over movement for that patient. We're able to look at now those power spectral densities over time. So this subject, month 1, month 3, month 6, month 12, and we can see that there's with the exception of this first month, we can see that there's a stability of the signal after the first month in these power spectral densities. So we have a reliable signal. It's not just something that's random from day to day. It's reliable and stable. And then we're able to look at the local field potential in therapeutic electrodes, or the electrodes that have been selected by the neurologist to treat the Parkinson's disease, and non-therapeutic electrodes, which are the remainder. And just taking one example here, subject 3 on the right side, the solid lines here are the therapy electrodes, and the dotted line here is the non-therapeutic electrode. And you can see that there's a big difference here in the beta strength, 13 to 30 hertz. That beta frequency, that low frequency that we talked about, is much greater in the therapeutic electrodes. So this could actually potentially even be a way to choose which electrodes to stimulate in challenging cases. One interesting thing we found is we wanted to look at the idea for is beta frequency pathological in Parkinson's disease, and so we looked in our recordings on medication and off medication and just looked at time averaged beta strength across therapeutic electrodes. We weren't actually able to see a significant difference between on and off medication beta change, beta strength. And that may be that some of these error bars are quite large. But we really weren't able to see in our recordings that there was this significant decrease in beta power with levodopa medication. And that kind of dovetails into this slide, where we wanted to see those spectrograms that I showed you in the beginning. We wanted to see if those patterns changed on and off medication. And it was my hypothesis going into this that giving patients levodopa would kind of wash away some of the beta effect that we're seeing. So we were trying to record most of these signals actually off of medication in order to kind of reproduce our spectrograms that we had from our intraoperative data. But we were kind of getting kind of weak spectrograms, to tell you the truth. So this is an example of well, let's take this patient here, subject 3. This is an example of our off medication recording. So these are off medication here at the bottom row. This is a left hand movement, so a left button press. And you can see there's not a whole lot of impressive beta change or high frequency change with the left button press. But when we later did the same experiment on medication, which is this upper row, we see a much stronger beta suppression actually on medication than we do off of medication. And associated with that, there's some high frequency or gamma change that we see with that behavior, which is a little bit more consistent with the literature that gamma change is augmented with levodopa medication. And we saw that in multiple patients. I mean, we can look at this other subject 2. There's increased high gamma change with a button press on medication, where we don't see it as much in off medication. And this beta change that we see here on medication gets kind of washed away in the off medication state. And same thing here, a nice large beta. Well, this is a little anti my hypothesis, but in this case we have a larger beta change off medication. So there is some variability there for sure. And then this is the same analysis, but with a different behavior. So this is a reach behavior where subjects are reaching their arm and hitting a target, which is a little bit more of a gross motor movement, takes a little bit longer, involves a bigger part of the body. So you can see that the effect size is much greater. And here, time 0 is when they actually hit the target, so it's at the completion of the act. And we can see here, subject 2 on medication, significant beta suppression with that movement, significant gamma high frequency augmentation on medication, but that is not seen in the off medication state. So really, this type of analysis leads quite well to more advanced experimentation looking at these signals. We're now able to do more complex gait analysis in our gait lab and looking at our signals while patients are actually up and walking and turning. We're able to look at these signals on and off medication, and we're able to evaluate these signals when patients are doing longer time period cognitive tasks, such as verbal fluency and the typical neuropsychological batteries. So I think this is really going to open the door for us to be able to really see the involvement of these signals from the subthalamic nucleus in all of these behaviors. So thank you very much, and appreciate any comments.
Adam, thank you very much.